Hey there, awesome physics students. Let's talk about how tension works. Tension seems fairly straightforward, but actually you can easily come to it in a problem and be really confused on how it works. The main principle that we're going to talk about in tension is that in one rope, the tension throughout the rope is the same and it always pulls. So that is what we're going to use throughout here. Let's go through some examples to help you get unconfused. The first example is really simple. We have a scale, and I'm going to draw all the scales. I'm going to draw our circles like this, and I'm going to use a string to hang a mass from the scale, and that mass, the weight of that mass is 10 newtons. And so, what is the scale going to read? Well, I think you can easily see it's going to be 10 newtons. But how can we see this with physics to be sure? Well, if I draw a free body diagram for this mass, there's going to be a 10 newton weight down, and then this is attached to a rope, so there's going to be a tension up. And if the acceleration of this mass is 0, then the tension is going to be equal in magnitude to the 10 newtons, so that the sum of the forces are 0. And so the tension in this rope is 10 newtons, and then therefore this rope pulls on the scale with 10 newtons. Okay. Let's do another example. In this case, I'm going to take the scale and I'm going to turn it sideways, and I'm going to attach it to a rope and run that rope over a pulley, and then I'm going to attach it to another 10 newton weight. And so I think you can easily see based on this scenario that the tension in this part of the rope is going to be 10 newtons. If I run it over a pulley, remember it's the same rope, the tension is the same throughout the rope, and it always pulls. So the tension up in this part of the rope, because it's the same rope, is still 10 newtons, and it still always pulls. And so it's going to pull on the scale, and this scale is going to read 10 newtons. If I modify this and ran this rope instead around another pulley, and then I attached it to the scale, and the scale is now upside down, then again, this part of the rope would have a tension of 10 newtons because it's the same rope the whole way out, and it always pulls, and so this is going to pull on the scale, and this scale is going to read 10 newtons. And I'm sorry, I can't draw upside down, so just going to write that right side up. All right, let's do another situation, a little bit harder one. Let's have two scales here, and we're going to attach those two scales together with a cord, and we're going to run that cord over a pulley, and that pulley is going to support a mass. So this is a pulley right here. The question, and of course this is again a 10 newton weight. The question is, what do each of these scales read? Well, in this case, you want to remember back to some of the things we talked about before, where you want to be careful about choosing the object that you're going to look at the forces of. And so we want to, for the object we want to look at the pulley and the mass together. And if we look at a free body diagram of those together, we see that there's going to be a 10 newton weight down, right? That's all there is. But now we see that there's two tensions up, and remember the tension always pulls. And so we're going to get a tension from this rope and a tension from this rope, and we have two of them to offset the 10 newtons. So of course these are going to be 5 newtons each. You can see that based on the acceleration being 0. Okay? All right, let's do another scenario here. Imagine we have one scale, and now we attach that scale to a pulley of its own. And instead of, and then we're going to have two masses instead of two pulleys. So let me just offset these masses so they don't interfere with each other. So these are 5 newton masses in this case. And the question now is, what is this scale going to read? Well, there's a couple of ways to get at this one. One way is to note that, look, the scale knows that it's being pulled on, and it knows it's supporting 10 newtons of weight total, and it doesn't care how the weight is distributed into 2 pieces or 20 pieces or whatever. It's going to read 10 newtons because it's supporting 10 newtons of weight. That's true. Another way to do it is to look at the object for the free body diagram, make it be the scale with the pulley together. And in that case, you're going to see that there's going to be two tensions pulling down, and those are going to be 5 newtons each, right? Because the tension here is 5 newtons, And this is the same cable, so the tension over here is 5 newtons. And remember, they always pull, so these are going to pull. And then there's a cable here, and that one, the tension in there is going to be what the scale is going to read. And that tension, of course, there's only one of them offsetting the two, and so that tension has to be 10 newtons. And so that's going to pull on the scale, and the scale is going to read 10 newtons. Okay? All right, one more example. This is kind of a cool one. I like this one. Imagine we have a ceiling, and we have two situations with the masses attached to the ceiling. In both cases, I'm going to amp up these masses a little bit. Let's make them bigger. This is 100 newtons. And in this case, I'm going to pull up on it with some force. And there's just one rope attached to the ceiling. And in this case, I'm going to attach a pulley to the ceiling. And I'm going to pull on this with a force 2. And I'm going to support, again, I'm going to support a 100 Newton weight. So the question here is, which one of these forces is going to be bigger? Just to hold it there. So in both of these cases, my acceleration is going to be 0. Well, I think if you see in this one, of course, the tension there is going to be 100 newtons, right? This is the same rope, so this tension must be 100 newtons. In this case, if we draw a free body diagram for the 100 Newton mass with the pulley, like we did before, we'll see that the weight down is 100 newtons, but there's two tensions pulling up. And so each of those tensions can be 50 newtons. And so the tension here is going to be 50 newtons less. Now here's one more question. In which of these two cases is the ceiling more likely to break? I think in this case you see that there's one tension of 50 newtons pulling down on the ceiling here. Whereas here, if you think of there's a tension here pulling down and there's a tension here pulling down, and each of those are 100 newtons. So there's a total of 200 newtons pulling down on the ceiling in this case, where here it's only 50 newtons pulling down on the ceiling. And so in this case, it's much more likely to break because it has 4 times as much force pulling down on it. Okay? Hopefully this helps you become unconfused with tensions. Just remember the tension is the same throughout the rope and it always pulls.